Hey team, today we're going to be talking about the movement of molecules, but before we get to that, I want to refresh your memory a little bit about the cell membrane. As you all remember, we have a fluid mosaic model here, so we've got our phospholipid bilayer right here, and then embedded within it are a bunch of transmembrane proteins, and we've got sugar lipids and sugar proteins also embedded within cholesterol molecules. And so this is a fluid model. All these elements are moving around within the plasma membrane. And the primary purpose of the plasma membrane is to create a barrier between the extracellular space and the intercellular space, what's inside the cell. We want to create a barrier so that we can have a different set of conditions inside the cell as compared to outside the cell. And that's because inside the cell we're going to be having lots of chemical reactions that are going to power life inside the cell, and we want those to be within a certain set of conditions. So we need to control, or our cell needs to control what's happening inside and the materials that are inside the cell, and keep that stable as compared to the outside, which is going to be crazy, who knows what's happening out here. So the main goal of the cell membrane is to create a barrier, and that's to maintain homeostasis inside the cell. I'm going to write that down. So our cell wants to maintain homeostasis, a constant internal environment amidst this crazy and changing external environment. Okay, so our plasma membrane is controlling what comes in and out of the cell, and as I said before, it's a fluid mosaic model. So things are flowing, and all the time, small gaps within our membrane are opening and closing. And so stuff is coming in and out. But the cell is selectively permeable. So because of the nature of this bilayer, which is both hydrophilic right here and hydrophobic in here, the membrane is choosy on what it allows to diffuse through it. So we've got this idea of selectively permeable. Only certain types of molecules will be allowed to come inside through the membrane. Okay, so I think that's the background information you need to know before we start. A few more things. Okay, so we're going to be talking today about the movement of molecules. And as you probably remember from chemistry, molecules are always moving. So we've got this idea of molecular motion. And molecular motion tells us that everything is moving. So imagine we have a steel brick right here. We know that this little brick is composed of lots of little molecules. If we were to zoom way in on this brick, lots of little molecules all stacked up nice and neatly next to each other. And all these little molecules are vibrating in space, in this restricted space, but still they're moving in here. And if we were to have a container, let's say filled with some sort of liquid in here, we know that there would be molecules making up that liquid as well, and they would be a little more spaced out than the molecules we see in our steel brick, but they're also moving, just like our brick is moving, and they're moving a little faster. And again, if we were to look at a beaker that we say, oh, this beaker is empty, but it's actually not, it's filled with gas molecules. These are even further spaced out, and they're moving even faster than the water molecules. So there's this idea that particles have this inherent motion, and the craziness of their motion depends on the state that they are in. So inherent molecular motion. That's an important concept here too. So let's imagine for a second, let's zoom back in here again, that you have a beaker of perfume. And perfume is a volatile compound. I don't want to put a cap on it. I'm going to put some perfume in here. And it very easily evaporates. So when you have perfume and you open it up, and you put the cap on the side, draw the cap over here. You open it up, perfume molecules are going to come out of solution, and they're going to evaporate into the air. And there's going to be this area of really high concentration around the beaker itself. And I'm going to write H here and put that in brackets. As you remember from chemistry, that is, the brackets mean concentration. So this area of high concentration right around the beaker, and then an area of low concentration further away from the beaker. But say you cap, I want to select the whole thing. You cap this perfume. So now our perfume is capped, and now these points will actually, I'm going to erase some of them over here. They are going to go from this area of high concentration to an area of lower concentration. Oh, I want red. So they're going to what's called diffuse down their concentration gradient. So if we had a bunch over here, we're going to see movement of these molecules down their concentration gradient, meaning they're going to go from an area of high concentration to low. And eventually what we'll see is that we have an equal amount of particles spread out throughout the whole room. So we're no longer going to have this area of high concentration and low concentration. Instead, we are going to be in a state of what is called, go away, silly thing. Okay, there we go. So if we now have an equal amount of particles diffused throughout the room, we've got, I've got mail, dynamic equilibrium. And this is the idea that all these particles, they're still moving. So, for example, this particle can move in any direction within the room, and the same with this one. But on average, we have the same concentration of particles over here as we have concentration of particles up over here. So although all these particles are still moving, on average, the concentration throughout the room is the same. And the second law of thermodynamics that says that all things trend towards thermodynamic equilibrium, greater entropy, is the force that's driving this to happen. So all things diffuse down their concentration gradient. Okay, so I think I set the stage here for what we're actually going to be talking about today, which is the movement of molecules in and out of cells. Okay, so let's move over a little bit to a new sheet, and let's say I have a beaker full of water and salt. So I've got water and salt in this beaker, and let's say, so you should know that water is going to be my solvent, and salt is going to be my solute, and together they are making up my solution if the salt is evenly distributed throughout the beaker of water, which I'm going to say it is. So let's say I have a solution that's composed of 98% water and 2% salt. Now I'm going to add a cell in the center of my beaker, and this cell has a selectively permeable membrane that is going to allow water to pass through it, but it's not going to allow salt to pass through. So the conditions of my membrane are such that water, H2O, can pass through it, so water can move in and out, and salt cannot pass. Cannot pass. Okay, and in my cell, the initial concentrations that we're starting out here is, let's say I have 95% water inside my cell, and that means I have 5% NaCl inside the cell. Okay, and remember, water can pass and salt cannot pass. So, what's going to happen? Well, right now we're not at equilibrium. Why not? Because the concentration of water and salt outside the cell is not the same as the concentration of water and salt inside the cell. So the cell is going to, the laws of thermodynamics say that the cell and the water are going to strive to reach thermodynamic equilibrium. But in this case, only water can move. And we're going to give a name to this movement of water. It's called osmosis. It's the movement of water. The water could be moving into something or out of something, doesn't matter. But osmosis is the movement of water. Okay, so in this case, because the concentration of water outside the cell is higher than the concentration of water inside the cell, and salt can't move here, water is going to move into our cell. And much like a balloon will blow up if you add air to it, this cell is going to expand as water moves into it. So our cell is going to keep expanding until the concentration of water and salt inside the cell are equal to the concentration of water and salt outside the cell. So what's going to happen is this is going to have to go up, and as a result, this will go down, and the cell in total will expand. So think carefully about this. The total number of particles of salt inside our cell hasn't actually changed. What's changed is the particles of water inside the cell, and therefore the concentration of the two, the relative ratio of the two, has changed because we've had water coming into our cell. Okay, awesome. So we have a special name for this type of situation. So this solution that we created here was actually a hypotonic solution, Hypotonic, hypotonic solution. This means that the number of particles of solute, this is salt in this case, to our number of particles of solvent, water in this case, of our solution was less than the ratio of solute to solvent in our cell. So a hypotonic solution is when, so we can also state this as the ratio of solute to solvent outside the cell is less than the ratio of solute to solvent inside the cell. Basically, there's a higher concentration of salt inside the cell than there is outside the cell. And that's what a hypotonic solution is. So, in the case of a hypotonic solution, we're going to have water, H2O, moving inside the cell. And we have a special name for this. It's called cytolysis, Cytolysis. And you can imagine if the concentration of the solute to solvent, the hypotonic solution, were so hypotonic to the cell, so the cell had a really high concentration of salt, and the solution outside was very watery, we'd have a large amount of water moving into the cell, and at some point our cell would burst. So in the case of cytolysis, if the concentrations are too different, we can have too much water moving inside of the cell, and the membrane can't hold all that, and it's going to burst. So now imagine a case where this is reversed, and we have what's called a hypertonic solution. So now if we look at our ratios of solute to solvent, before we saw we had less solute to solvent ratio on a low concentration outside the cell as compared to the inside. This time we're going to be seeing the opposite. So the concentration of salt outside the cell is higher than the concentration of salt inside the cell. And as a result, we're going to have water move out of the cell. And again, there's a special name for this. It's called plasmolysis, or plasmolysis. And just like cytolysis was kind of a dangerous situation for the cell, it could cause the cell to burst, plasmolysis is also a dangerous situation for the cell because it greatly dehydrates the cell. You can see all this water is moving out. Okay, this is getting to be quite a long screencast, so I'm going to cut it off here. But I hope you have a better understanding now of movement of molecules inside and out of cells, and the idea of a selectively permeable membrane and why molecules are moving in and out. It's the laws of thermodynamics that are driving them towards dynamic equilibrium. Okay, over and out.